What happens when you push a pendulum in exactly the right rhythm? We spent 2 days at the workshop finding out with sensors, robots, and a lot of math. I'm Alan.
I'm Maya. And I'm Karen.
I'm Asher.
2 days, 2 experiments. Day 1, measure how a pendulum's speed depends on its length and test the theory formula. Day 2, force a pendulum with a spinning robot and a spring to hunt for resonance, the exact frequency where tiny pushes create huge swings.
On the first day, we built a pendulum out of Lego and mounted a smartphone on it. So the phone's own gyroscope sensor rides the pendulum and measures its angular velocity, which is how fast it rotates as it swings. We block coded an app that reads the gyro and gravity sensors live and draws the graphs in real time. Then we tested the 4 pendulum lengths, 12, 30, 50, and 70 centimeters, with 4 trials each, 16 runs total. The app put sine waves on our graphs, one for the pendulum's angle, and one for its angular velocity from the gyro. From every fit we read, omega, how fast that pendulum oscillates, and the fits showed the swing slowly shrinking over time. That's friction dampening the motion. Now here's every single trial on one graph. We have 16 runs across 4 lengths. And now the theory. Omega of L equals the square root of G over L. That's the purple curve. Comparing our measured averages to the calculated values, at 50 centimeters, we were off by just 0.16%, and 30 centimeters, 1.1%, and 73.5, and 12 centimeters missed by 8.3. The phone's own size matters most on the shortest pendulum. The average error was around 3%. The formula holds. Our 4 trials at each length agreed with each other to within about 1 to 3%, and the averages closely matched the square root of G over L prediction. For a hand-built rig and a phone sensor, that's a really good confirmation. On the second day, we worked on resonance. We built a new pendulum hanging from a Lego bridge between 2 tables and connected it through a spring to a motor cranking in a circle. The motor delivers a periodic push at whatever frequency we choose, a forced oscillator built out of Legos. Then we swept the driving frequency. Far from the natural frequency, the pendulum barely reacts. But as the robot's rhythm approaches the pendulum's own, the swing explodes. That spike in the data is resonance, maximum energy transfer at one special frequency. The amplitude follows this curve, f0 over the square root of omega 0 squared minus omega squared, all squared, plus the damping term, which is pretty much just friction. The peak sits at the natural frequency, and our measured peak matches the predicted one. Omega measured equals omega predicted. This is the same physics that collapsed the Tacoma's narrow bridge. The reason glass shatters when you sing at a certain frequency, and how your microwave heats food. Resonance is everywhere. We just built it from scratch and measured it. 2 pendulums, 1 phone, 1 robot. And the math held up. Thanks for watching.